It's all yours.
Okay, thanks a lot. So, good afternoon, everyone. First of all, I would like to deeply thank you for taking the time to attend this seminar, and I hope that you will find it interesting and useful at the same time. For those who don't know me, again, my name is Karim Aljawhari, and I'm a PhD student at the University of Pavia in Italy. And today, me and Dr. Roberto Gentile are going to present our recent research work, which in fact represents two independent studies, but at the same time, they are highly correlated and interconnected. The first topic discusses about the effects of ground motion sequences on fragility and vulnerability of case study reinforced concrete frames. This study has been completed by myself in collaboration with Dr. Carmen Galasso, who is my supervisor, and Roberto Gentile and Fabio Freddi. We submitted a paper about this research work, which has been recently accepted for publication in the Journal of Bulletin of Earthquake Engineering. But in any case, let's begin our talk right now, and we would highly appreciate your comments and your questions at the end of the presentation. So just to give a quick background, I believe that we all understand that ground motions can occur in the form of sequences, which can take place in many forms, like for instance, the main shock-aftershock sequences or the triggered events sequences. And unfortunately, the sequential ground shaking in general can lead to a severe damage accumulation and a faster degradation for the capacity of the buildings. And on the top of that, the seismic sequences are usually occurring within a very narrow time frame that is not sufficient at all in order to do major repair works in case you have a damaged building population. And this unfortunately can lead to a catastrophic consequences as demonstrated by many past events. If you take a look at this figure here, you will see a building located in central Italy, which was hit by a main shock in August 2016. So I think we can see in the figure that this building is damaged, but at least it remained stable. However, 2 months after that, and particularly in October 2016, the same building was hit by an aftershock, which by the way was weaker than the main shock, but it led at the end to a complete collapse. And therefore, in general, the effects of ground motion sequences on the buildings have attracted a lot of research efforts in the past, during the past decades, but the studies available in the literature that are pertaining to the assessment of the fragility and particularly vulnerability using refined nonlinear models are still very few. So in this study, we try to fill this research gap by investigating the effects of ground motion sequences on the performance of case study reinforced concrete frames. We also try to produce what we call the state-dependent fragility functions that account for the presence of initial damage in our case study frames. And finally, we endeavor to develop the vulnerability functions both in 2D and 3D forms that can be easily adopted in seismic risk assessment and direct and quantification of direct seismic losses applications. The methodological framework that we followed starts by identifying the case study buildings and developing the relevant nonlinear models. After that, we select an appropriate engineering demand parameter that we can measure in order to quantify the damage, and we calibrate what we call the damage states. Next, we select an appropriate measure for the ground shaking intensity, and we define the ground motion sequences because after that, we are going to perform nonlinear time history analysis. Then we use the analysis results in order to fit a probabilistic seismic demand model that can be used later in order to derive the state-dependent fragility curves. After that, we can go from the fragility curves to what we call the vulnerability functions, which can be expressed in the form of 2D curves or even 3D surfaces, as will be explained at the end of this presentation. Let's start by defining the case study buildings. So first, we considered a non-ductile pre-code moment-resisting frame, which is made of reinforced concrete, and it has been designed only to sustain the gravity loads in accordance with the Royal Decree in Italy of 1939. Here you can see an elevation view of the frame that, as you can see, it consists of 4 floors, and it has a uniform bay length of 4.5 meters. Here you can see a cross-section for the beam and another cross-section for the column. Next, we considered a ductile special code moment resisting frame that has exactly a similar geometrical layout to the previous frame, but this time it has been designed according to the seismic provisions of the Eurocode 8 for the buildings with high ductility class. So here you can see an elevation view of the frame together with a beam cross-section and a column cross-section. I would like also to add that we considered both the pre-code frame and the special code frame in both bare and infill configurations, which means that on total, we have 4 different case studies. The first one is the special code bare frame. The second one is the special code infill frame. Number 3 is the pre-code bare frame. And finally, we have the pre-code infilled frame. Now, regarding the nonlinear modeling approach, we developed 2D nonlinear models using OpenCEGE software, and we also implemented the lump plasticity approach, as you can see in the below figure. Now, in order to account for the different modes of failures and different nonlinearities, we decided to model flexural and shear springs that are placed together in series, as you can see on the right-hand side of the figure. We also accounted for the presence of infills using the concept of equivalent struts, as you can see on the left-hand side of the figure. So in order to be able to measure in order to be able to quantify the different damage levels that my structure can experience during an earthquake, we defined 3 different levels of the damages, which are called the damage states. So the first one is damage state 1, that represents the slight damages, damage state 2, that represents the extensive damages, and damage state 3, that represents the near collapse state. And of course, it's the most severe one. Now, after that, to be able to numerically quantify this damage, we decided to use the maximum interstory drift ratio as the main engineering demand parameter, because it has been proven that it's highly correlated with structural and non-structural damages. And based on that, the next step will be calibrating the maximum interstory drift ratio thresholds corresponding to the occurrence of each one of the damage states that I talked about earlier. This simply, without going through too much details, this can be simply done by running the pushover analysis and then doing local assessment of multiple measurable criteria in order to spot the exact occurrence of each one of the damage states in terms of drift thresholds. So on the left-hand side, you can see the special code frames, their pushover curves, together with the damage state thresholds. And on the right side, you can see the same parameters for the pre-code frames. Let's talk now about the selection of ground motion sequences. So first of all, I would like to highlight that we selected the average spectral acceleration as a measure for the intensity level of the ground shaking for all the ground motions that we have. Now, regarding the sequences approach, we implemented what we call the artificial ground motion sequences. And according to that concept, the main shock records are going to be used as both main shocks and aftershocks. And in order to minimize the bias associated with this approach, it's always preferable to select the main shocks randomly in order to be seeded as aftershocks. Now, I know that many people might argue that in this case, maybe using the real sequences that consist of real main shocks and real aftershocks might be better to assess the response. But the main problem here is that the aftershocks with high levels of intensity are quite scarce, which means that there might be some problem in terms of statistical stability of the fragility curves. And therefore, for the reason of our research, it's always preferable to implement the artificial sequences in order to assess the response and derive fragility functions. In any case, each artificial sequence, we assume that it consists of 2 ground motions. The first one is called GM1, and the second one is called GM2, as you can see in this figure. In order to perform this selection, we first picked the main shock records from 3 different databases that are available online, as you can see in this slide. And after that, we removed all the weak records of the main shocks that practically have no engineering significance to our analysis. And we ended up having around 500 main shock records. Now, in the ideal case scenario, if I'm interested to form artificial sequences, I'm supposed to combine each main shock record with all the rest of the main shocks, as you can see in this figure. So on the x-axis, you can see the intensity level of ground motion 1, and on the y-axis, you can see the intensity level of ground motion 2 for each sequence. But if I implemented this ideal scenario, I will end up having 250,000 ground motion sequences, and of course, this is computationally expensive. And therefore, in order to reduce the number of selected sequences in an unbiased way, we decided to randomly assemble those sequences using the Latin hypercube sampling approach. And we ended up having only 500 ground motion sequences that are, as you can see, covering a wide range of intensity levels, and of course will require much less computational effort. Let's begin now the discussion about the analysis. So our analysis are divided into two stages. Stage one has to do with the buildings in the undamaged states. So they are initially as built without any initial damages. So in that stage, the models are going to be subjected to ground motion one only in order to assess their performance in the undamaged conditions. So here you can see the cloud analysis results that show on the x-axis the intensity level of ground motion 1 with the corresponding maximum interstory drift ratio from ground motion 1. And this is for the special code frames. And this table shows us the distribution of different damage states. The same can be done for the case of the pre-code frames, and those are the clouds. And this is the distribution of the damage states shown in this table. We can use these clouds in order to fit linear probabilistic seismic demand models in order to derive what we call the fragility functions that are shown here. So on the top, you can see the fragility curves for the special code frames, and in the bottom, you can see the fragility curves for the pre-code frames. For those who don't know the fragility curves, they are actually useful because they provide us with the probability of exceeding a specific levels of damage states given the intensity level of the ground motion. What we can notice here is that the special code frames are significantly less fragile in terms of are significantly less fragile than the pre-code frames because practically they showed a better performance during stage one analysis. Let's move now to the most important stage, which is stage number 2, that has to do with the damaged buildings. So in that stage, the models will be subjected to the full sequences that include both ground motion 1 and ground motion 2 in order to investigate the effect of the initial damage caused by ground motion 1 on the vulnerability and fragility of the case study frames. Now, in this case, to be able to derive the fragility curves for the case study buildings, which are initially damaged by ground motion 1, we have to produce new clouds as per the following steps. So, first, we have to separate the clouds resulting from stage 1 analysis based on the initial damage state caused by ground motion 1. So let's say that I have this cloud resulting from stage 1 of the analysis, and this is from the special code bare frame. For instance, I can go to the green cases that represent damage state 1 caused by ground motion 1, and I will take them and plot them in a brand new cloud, as you can see in the following figure. But we have to pay attention that at this time, the intensity level will be the average SA of ground motion 2 rather than ground motion 1, and the engineering demand parameter will be the maximum interstory drift ratio resulting from ground motion 2 rather than ground motion 1. And in this case, I will be able to produce new clouds that are conditional on the initial damage state caused by ground motion 1, and I can use them to derive the state-dependent fragility functions. But please pay attention here that in the ideal case scenario, the maximum interstory drift ratio resulting from ground motion 2 is supposed to be higher than that resulting from ground motion 1 in order to have an indicator that there is a damage increase. But the main problem here is that the maximum interstory drift ratio is only a peak parameter that does not explicitly measure damage accumulation during seismic sequences. And based on that, many analysis cases showed me an opposite observation, which means that the maximum interstory drift ratio resulting from ground motion 2 is less than that given by ground motion 1. And this represents a false indicator that the damage level achieved during ground motion 1 will be reduced after we apply ground motion 2, which physically doesn't make any sense because whenever you apply a new ground motion to your structure, you're supposed to get an increased level of damage, even if that increase in the damage is a little bit. And if we use those analysis cases in the fragility derivation, we might encounter what we call the crossing of the fragility curves. And again, this crossing is giving us a false indicator that the buildings which are having initial damages due to ground motion 1 are actually less fragile than the buildings that have no initial damages at all, which doesn't make sense as we all understand. However, we interestingly noticed that those analysis with cases with the false indicators happen only in the sequences that are characterized with the low levels of intensity for ground motion 2. And according to that, we decided that it's more appropriate to use the bilinear probabilistic seismic demand models rather than the classic linear ones. Why is that? Because simply they are more representative for the physics of the problem. Because basically, they allow us to account for two different trends in the structural response. So there will be a trend for the cases characterized with low intensity levels and another trend for the cases characterized with high intensity levels. To explain that, please have a look at this figure. I think we can notice that the continuous gray line, which is the classic linear model resulting from stage 1 analysis, is having an intersection with the red dashed line, which is the classic linear model that can be fitted from stage 2 analysis. And this kind of intersection is what will cause the crossing of the fragility curves that we talked about in the previous slide. However, if we use what we call the bilinear probabilistic seismic demand model, which is shown here as a dashed black line, we can notice that in this case, we are accounting for the performance and the structural response in a better way by accounting for the two different trends. And at the same time, we avoid the problems of the crossings. And therefore, we were able to derive the state-dependent fragility curves, as you can see in those figures. Now, in order to explain things here, the continuous line represents the fragility curves for the buildings that are undamaged at all in their original conditions. And the dashed lines and the dashed dotted lines represent the fragility curves for the buildings that are initially damaged by ground motion 1. We can see here that the fragility curves are shifting to the left whenever I have an initial damage in my buildings, which clearly indicates that the presence of initial damage will increase the fragility of the buildings. So in order to give a sense of numbers, when the structures were initially in damage state 1, the fragility is increasing between 10% to 20%. On the other hand, when the structures are initially in damage state 2, the fragility is increasing between 32 to 42%, which is significantly more considerable than the previous case. This is a clear evidence that whenever you have a more initial damage, it means that the structures becomes more and more fragile accordingly. The final step represents the derivation of the fragility functions, which can be done by combining the fragility curves that we discussed earlier with the so-called damage to loss ratios using the total probability theorem. For the reason of this study, we used properly calibrated damage to loss ratios, which are based on studies of microseismic damage observations, as you can see in the following table. So accordingly, we were able to derive the vulnerability functions that provide us with the expected seismic losses, which is the most important thing for us, given the intensity level of the ground motions. Again, the continuous lines here represent the vulnerability functions or the loss functions for the buildings in their original conditions without being initially damaged at all. And the dashed lines and the dotted lines represent the vulnerability functions in case the buildings are having initial damages due to ground motion 1. If we note something here, you can see the big difference in terms of losses for each single value of intensity level, because whenever you have initial damage due to ground motion 1, the losses or the expected seismic losses will increase drastically in case another ground motion hit your structure. Another useful way to represent the vulnerability is to plot them in the form of 3D surfaces. In this case, on the horizontal axis, you can see the intensity level of ground motion 1 and the intensity level of ground motion 2. And on the vertical axis, you see the loss ratio, the expected loss ratio, or the seismic losses, the average seismic losses that are expected in the building. So all what we need here is just the intensity level of the first ground motion, and we can estimate an initial loss ratio. And we need also the intensity level of a second ground motion that we can use to estimate the new loss ratio, which will be greater than the previous one due to the presence of additional damage. Those kind of surfaces can be easily implemented in seismic risk exercises and application because they help us in a very fast and a good way to estimate the additional losses that are caused by ground motion sequences rather than a single ground motion. Just before leaving the mic to Roberto, I would just like to end the slides by few remarks. So we could observe that the presence of initial damage due to ground motion 1 will definitely increase the fragility and the vulnerability of the case study frames. And also we noticed that when the initial damage state is higher, then the increase in the fragility and the vulnerability becomes very significant. And finally, we could observe that the special code frames are significantly less susceptible to ground motion sequences damages, unlike the pre-code frames. Thanks a lot for listening, and now I leave the mic to Roberto. Roberto?
Okay.
Floor is yours. I stopped sharing my screen.
I'll try to share the screen. Share, and where are you? This one. Can you see my presentation?
Yes, perfect.
Yes.
Okay. So thanks very much for this invitation and this opportunity to Arash and to EPICentre. And I will try to address the same issue Karim was trying to address using drift, but this time using hysteretic energy. So we basically discussed now why we like big quantities like drift when we derive fragility. And this is because we have many experimental tests based on drift that allow us to compute the demand and the capacity of our members and therefore our structures with reliability. However, whenever we have low cycle fatigue in our problem, we might lose some power from these peak quantities. For example, whenever we have long duration ground motions or very soft soils or ground motion sequences, which I will now call just as names main shock after shock, but in reality is ground motion 1, ground motion 2, as Karim has discussed. So whenever we use drift to have main shock after shock, unless we do some tricks like the bilinear probabilistic seismic demand model, as Karim has said, we might have crossings, which are basically statistical inconsistencies of our fragility model. I will try to address the issue using the dynamic hysteretic energy, which always increases. So you will never have a decrease of energy between aftershock and main shock. But we have a few challenges that we have to discuss first. So objectives are to discuss the trend between hysteretic energy and peak deformation, then to propose a probabilistic seismic demand model that works in main shock aftershock conditions, and then to provide a model to derive state-dependent fragilities based on energy. I'm sorry, I will have to use a few equations in my presentation, but I will try to minimize. So this one is very common, is the equation of motion. So I will not discuss it properly, so I'm sure you know it. And the only thing is that you can express this in integral terms such that the third term over there is the hysteretic energy. Actually, this term also comprehends the elastic energy, but if your structure comes to rest after the ground motion, the elastic energy goes to zero, and therefore that term is the dynamic hysteretic energy, which by the way is the area under the dynamic force displacement response of your system. So if you look at the equation, you see what are the parameters that influence the hysteretic energy. Of course, the force displacement response, the mass of the system, the viscous damping, and most importantly, the load hystery, so the ground motions you choose. You dig a bit deeper and you see that the force displacement response might depend on the backbone you use, so the capacity of your system, the degradation of stiffness, so the hysteretic rules, and then the degradation of strength within a cycle and cyclic. If you go to a real structure, you see that all these parameters depend on the material of your structure, the lateral resisting system, so a frame versus a wall or a dual system, etc., the modal properties for which the height might be a good proxy, or the plastic mechanism of your system for which the construction year might be a good proxy. So it is clear that we can never have general results for the peak deformation versus hysteretic energy relationship for any structure. However, whenever we select one structure or we select an archetype structure, all these parameters are basically fixed, so we can derive considerations, provided that we properly characterize the load history, so the ground motions we select. And one way to do it is exactly what Karim was doing before, so to have assembled sequences using real ground motions, so that you can cover with, in this case, Latin hypercube sampling, you can cover a wide range of intensity of your ground motions in the main shock you see in the axis, in the x-axis, and the aftershock in the y-axis. And I'm showing here that I selected 1,000 sequences which are giving me a wide range of both the average SA on the left and significant duration on the right, which are the most important parameters to consider in this case. So let's consider a realistic frame. This is a concrete frame for stories 4 bays. And this is a newly designed one. So you have plastic hinges everywhere at all stories and plastic hinges in the columns at the ground. However, whenever you calculate the cloud analysis only considering the main shock, on the left, you have the maximum interstory drift versus the hysteretic energy in the main shock. And you see that this data fits the power law relationship that we always use. And this power law relationship, the black curve on the left, is the median energy versus drift response, allows us to convert drift threshold that we use to define our damage states or limit states in terms of energy-based ones. So we can have the same reliability of the drift measures, but we also have the thresholds in terms of energy, which we will need to define the fragilities. Then we try to filter, as Karim has done before, the cloud analysis of the main shock, considering the damage state that we achieved. So let's get an example. I get all the yellow dots here that are the analysis leading to damage state 2 in the main shock. And I compute new clouds using the aftershock only data. And I can fit another power law model between aftershock drift and aftershock hysteretic energy, which depends on the damage state of the main shock, so that I can immediately find that the overall slope of this power law goes down the higher the damage state in the main shock is. So what does this mean? That the more my structure has dissipated energy in the main shock, the less will be able to dissipate energy in the aftershock for a given value of the peak aftershock drift. So the more I dissipated, the less I can dissipate. This property will be very, very useful in building our probabilistic seismic demand model, which is a surface, in this case, representing the energy, hysteretic energy, cumulative on the main shock and aftershock. And this will depend on the maximum interstory drift in the main shock and an intensity measure of the aftershock. In this case, the intensity measure is average SA. What I require from this model, I require it must be consistent with the mechanics of main shock aftershock sequences. So this is basically considering that the hysteretic energy must be monotonically increasing. I can never decrease my total dissipated energy by going from the main shock to the aftershock. This is somehow trivial. Then I want the aftershock hysteretic energy to be decreasing with the maximum interstory drift achieved in the main shock. Is exactly what we said before. The more I dissipate it, the less I can dissipate. Then I also want the model to be a generalization of the common power law relationship that we use for single clouds, so that if I can derive fragility functions of the main shock only from this model, I should get the same result I get with normal power law approach. So let's decompose the issue in main shock first and aftershock later. First of all, we've seen that before. I can fit for the main shock only a power law relationship, the blue curve there, using the main shock only data, drift versus energy, that derives the median response of the main shock energy. And I can derive the A and B parameters over there via linear regression. That's a trivial part. For the aftershock part, we need a consideration first, which seems complicated, but in reality is trivial. So let's imagine you have a main shock producing zero drift, zero maximum drift, which means there is no main shock. Then you attach to this ideal main shock an aftershock. Whatever you have, and you call it aftershock, is in reality the main shock. So to put it into another way, an aftershock that follows a main shock producing zero drift is the main shock itself. Why all this? Because by using this consideration, I can use the main shock data in this plot over here, so the gray dots, by considering that for drift equal to zero, main shock drift equal to zero, so I have this plane over here, I can use the main shock data even if in my model I am considering the intensity measure of the aftershock due to this consideration. So I can fit the black power law model between the intensity measure and the hysteretic energy using the main shock only data. And I will get two parameters via linear regression, which are C0 and D. Then I, of course, need to consider that the overall slope of my power law model needs to go down the higher the main shock drift is. So one way of doing it is to have a coefficient C that depends on the drift in the main shock. And the easiest way of doing it is to have a linear damping factor, which is like simply 1 minus a parameter m times the drift that multiplies the old C0 that we already had. And to calibrate this parameter m, I can use the red dots, which are the aftershock data. And this time I will use the triplets. I will use maximum interstory drift in the main shock, intensity in the aftershock, energy in the aftershock to calibrate this relationship via nonlinear regression so that I have m. This might be a bit confusing, so I will try to recap for a second. So I'm dividing up the energy in two parts, the main shock and the aftershock one. And first of all, I will use the main shock only data, drift versus energy, to estimate the parameters A and B very easily to get this power law, the blue power law. Then I will use again the main shock only data. So the intensity versus the energy to estimate C0 and D. So I can estimate the power law in black over here. Then I will estimate the parameter M that reduces the slope of this power law as the drift in the main shock increases with nonlinear regression based on the red dots over here, which are the triplets of maximum interstory drift in the main shock, intensity in the aftershock, and energy in the aftershock. I sum up those two surfaces and I get the final probabilistic seismic demand model that you see here. And this guy is basically giving me the median response of my structure in terms of energy. So that if I want a log normal fragility model, simply the median of the fragilities will be obtained intersecting these surface. In particular, I want fragility functions that express the probability of exceeding some kind of damage state in the aftershock conditioned on the pre-existing damage in the main shock. So conditioned on the damage state in the main shock. So how do I get the median over here? Let's assume we want the fragility of DS3 given a pre-existing DS2 in the main shock. So I consider the drift threshold for DS2, the conditioning damage state, and I intersect vertically this blue power law so that I get this curve that represents the conditioning curve on my model. Then I consider the drift threshold for DS3, and in terms of drift, I can convert it into energy terms using the same blue power law, and then I go horizontally until I intersect the yellow curve so that I can derive the median of the DS3 fragility given that I have a pre-existing damage state 2. Of course, you can define the damage state the way you want, and nothing changes here. So next step is to get the dispersion of these fragilities, and we decided to have the same dispersion for all the fragilities such that no crossings will occur. And this is the standard deviation of the logarithm of the residuals of your real data with respect to the model divided by the power law parameter D to get the log normal parameters. So the result will look like this on the right. So you will have a set of state-dependent fragilities, and in this case, I'm using the color to represent the final damage state, the damage state in the aftershock, and the line type to represent the initial damage state, so the damage state in the main shock. So for example, the dashed red line is the main shock DS4 fragility, so the undamaged DS4 fragility. Then, for example, the dashed dotted line over here is the damage state for fragility in the aftershock, provided that I already had a damage state equal to 3 in the main shock. So you can see there is a shift. So my fragility capacity of the structure, my median capacity, will be reduced, and I will have no, no intersection, such that my model is consistent and there are no biases. So let's apply this very quickly to a few case studies, just to have an idea. And for this case, I will consider 4-story, 4-base concrete frames, and I will have it frames of 3 types. First, I will have the beams-wave frames, which are newly designed. So you have global mechanism, all the beams and columns at the base, easy. Then you have very old frames with columns wave behavior, so a soft story at the ground. And then you have some kind of in-between condition for which you have an under-designed frame, which is called a mixed sway, which is not prone to soft story, but is generally failing because of shear failure in the joint panels. You take these three conditions and you infill them. You have the uniformly infilled configuration of these frames. And also you have the pillow-T configuration, which is like having infills missing only at the ground story. Of course, this results in a soft story behavior. I use the state-of-the-art lumped plasticity modeling for this, and I will not discuss it. Plus, I use the same 1,000 sequences that we discussed before, and the result are pretty much like this. So in the top left, you have the newly designed structure for which you see no shifts basically. So damage accumulation plays no role or so. The only exception is the damage state for fragility given a pre-existing damage state 3, which has a pretty much 25% shift on the left. This is not very, very relevant because the overall fragility of the damage structure is still very high. You have 1G average SA median, so not very relevant. You have the column sway case over here, and you have the highest shift in relative terms, but still not relevant because your structure is very weak anyway. The fragility capacity is very low anyway, so not very relevant. The most interesting case is the mixed sway one, for which you have the highest both relative and absolute shift on the left of the fragilities, and this shift also strongly increases if you consider the presence of the infills. So you have, for example, this DS4 fragility of 1G median that goes to approximately, I don't know, 0.3 median if you have a pre-existing damage state 3. So to wrap up, you can say that for a given archetype structure, the hysteretic energy versus peak deformation relationship is mostly dependent on the ground motion, with particular reference to the duration. The median hysteretic energy versus peak deformation relationship can be used to convert deformation-based damage threshold into energy-based one. Although this is consistent, we need experimental validation. So if you have ideas how to validate this, please let me know. And we provided a probabilistic seismic demand model and a set of state-dependent fragility model. And all this is consistent with the physics and shows no statistical bias. We provided a paper which is just out on EESD, which I can give you if you're interested. Thanks.
Thank you very much. Okay, so well done. Very interesting. We have a few minutes for some questions as well until people prepare themselves to ask the questions. If you don't mind, I'll ask you some questions. One thing, the building that you used is different than the building that Karim modeled.
Yes.
So you can't compare the final fragilities out of it.
No.
Okay. Is there any plan of doing that as well to see how different methods work?
You know, this is a good idea, but yes, we didn't think about it yet. But yeah,
okay.
thanks.
I don't want to put more pressure or work for you guys. One thing, the damage thresholds that you used before, like let's say the main shock and the aftershocks are the same, yes? You don't change the damage thresholds. Okay. And again, just one more question. How are you going?
On this, by considering that the damage state threshold do not change from the main shock to the aftershock, is like saying low cycle fatigue catastrophic failure is not accounted for. So provided you don't have snap of rebars or whatever, something very catastrophic due to low cycle fatigue, your threshold is mechanically based, you can demonstrate it, they don't change. So,
exactly. If the building doesn't change, it should continue as like the definitions that we always have. One thing is, where do you see these fragility curves to be
I agree.
used? Are they like the case of the worst case scenario fragility curves, or should we like get rid of all the fragility curves that we currently have, and we say, okay, there is always a chance of aftershock or another earthquake happening very close to our main shock, and we stick with these new type of fragility curves?
No, it turns out that for main shock only, the results of this model are very, very similar to whatever you can derive with drift. So you don't have to change whatever we did before.
Yeah, I mean the final outcome, the aftershock ones.
Well,
If
it
I want
depends.
to, exactly, so
It depends because there are cases in which you are more interested in damage accumulation. So, for example, for a new building, you basically don't care. And at least you can
yes.
demonstrate you should not care. That's important. For very, very weak buildings, again, yeah, you will have very strong shifts, reduction in capacity, but your structure is likely to collapse anyway in the main shock, so you don't care.
Mhm.
In the middle, maybe you care, but to be honest, I didn't think about the specific application of this. Is more of a proof of concept first, simply because I'm not 100% sure of the thresholds, because, as I said, this is consistent. You convert drift to energy, but still we need validations with experimental tests.
Mhm.
Yes, makes perfect sense. Carmina, I can see that you have raised your hand if you want to unmute yourself. And
Thanks, Karim, Roberto, for this. I just want to make a comment on one point that Karim made about the ground motion selection, because I know I saw Nevena is is listening, and so Karim said that he has selected artificial sequences, meaning simply pairing main shocks. Of course, you can do artificial sequences that are other consistent. So there is the recent approach by, for instance, Papadopoulos and Paolo Bazzurro, where they have developed some sort of target intensity measure for aftershock, given the target intensity measure for the main shock. And that, I would say, that should be the preferred approach, especially if you are doing set-specific and building-specific applications. So the motivating idea here is that we were looking mainly at regional type of applications for which you don't want to constrain your record selection to other consistent ground motions first, but also the really we were not looking at aftershock, just aftershock in a traditional sense. We were mainly interested in looking at sequences, in particular triggered events. So where ideally you can have that, a fault trigger through column stress transfer, blah, 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 trigger another event on a nearby fault, and not necessarily that correlation that is then so strong. So you can consider them as two independent main shocks in the extreme case. So I think that's an important comment because, again, Karim, I think, was very quick on that, say, okay, we use artificial sequences, simply pairing main shocks, fine. But again, there were motivations, and if you are doing a site-specific application, of course, the best way is to do some other consistent selection. And again, I think the Papadopoulos and Bazzurro's approach is definitely the current state of the art in that regard. Thanks.
Yeah, because simply they provide artificial sequences, but they are representative of a potential scenario of sequential ground shaking.
Yeah,
It's not
they are. That's, yeah.
spectrally compatible. Yeah.
Yeah. Thanks.
okay, anyone else has any question? You can raise your hand or you can type it in the chat. I can read it. And meanwhile, I have a question for Karim. It's not very much related to this aftershock, pre-shock, main shock, let's call it. How did you simulate the strength reduction of the infills, particularly in terms of shear?
Yeah. Okay. So we.
Because the model didn't show. The model was mainly on moment capacity, as far as I saw.
No. Let me show you. Can I share my screen quickly?
Yes, yes, yes.
All right.
As well as what happens if you have shear cracks in the frame itself, like in the middle of the column, for example.
So okay. Basically, the relationship that we use to define the backbone curve of the infills includes the degradation. It's the relationship developed by Liberatore and Di Canini. But
Oh,
if
I
you
just saw the spring. Yes, yes. Oh,
Yeah.
okay.
Yeah, so if you notice here, we have a diagonal strut and off-diagonal strut. The diagonal strut is just like connected between the geometric joints of the frame. So it provides like sort of contribution to the global seismic behavior of the frame. Now the off-diagonal strut is connected directly to the spring. So if there is like an increase of the shear demand, they might trigger the shear spring failure. And in this case, you will have a sudden collapse in the frame that you're analyzing.
And
So
that's,
yeah,
sorry, that shear failure will be in the frame members, like the columns and the beam.
the column. The shear is not modeled in the beams. It will be particularly in the column of that strut connected to the frame.
Okay, so any shear failure or any shear cracks inside the infill itself is kind of ignored.
The idea is you have to calculate like different failure modes of the infill, and the most critical one will be the prevailing one that you assume in the model. I mean, you cannot assume that the infills will crack by different modes inside the model itself. You have to pick one. And therefore, based on the properties of the infills that you have, you calculate the critical failure stress, like the tensile strain, the tensile failure, or the shear failure, or the compression of the diagonals. I don't know. I don't remember their names actually. But you select the most critical one in order to construct the relationship of the backbone curve for the infills. But in general, in your model, you assume that your infills, if they fail, they will have only one mode of failure. And it's an
fair
in-plane,
enough.
not out of plane. Yeah.
Okay.
Mhm.
Again, if anyone has any questions, let me just check the hour. Yeah. So if no one else has any questions, again, thank you very much for your presentation. Thank you very much for attending this seminar. I'll just share my screen for a second. As you all know, our next EPICentre seminar will be on Wednesday, 2nd of December, where Victor Mellati will be talking about dissipating systems for seismic protection of historic masonry structures. And after that, our next session will be before Christmas breaks, which Dr. Marco Bogueira will be talking about advances and challenges in tsunami assessment of buildings and critical infrastructures. Again, thank you very much for attending this session. Thank you very much for our presenters.
Thanks for hosting us, and we will for sure join the future meetings as well, because the presentations look very interesting, to be honest.
Yes, you're always more than welcome to UCL.
Thanks.
Thank you very much. Enjoy, keep safe, wash your hands. See you later.
Ciao, bye.
Thanks.